Hello, everyone. Time is up. Let's get started. As you all know, this is Tsinghua Alumni Academic Club's Distinguished Lecture Series, and we are in great honor of having Professor KJ Liu to be our speaker at this distinguished seminar. Professor KJ Liu is the founder, chairman, and the CTO of Origin AI that pioneers AI for wireless sensing and indoor tracking. I bet most of us know him. He's a distinguished scholar and also a wonderful entrepreneur. He's very recognized in a lot of different fields. He served as the 2022 IEEE President and CEO, IEEE Vice President for Technical Activities, and the President of IEEE Signal Processing Society, where he served as Editor-in-Chief for IEEE Signal Processing Magazine. He trained a lot of PhD students, and he has two very important products with us. Both Zhu Han and Jane Wang were his students, so they are now Vice President of TAAC. Thank you, Professor Liu, for training two wonderful colleagues of us. So we're also really happy to see Professor Liu is very successful in entrepreneurship. As mentioned earlier, he has the company Origin AI trying a lot of new things. He received a lot of awards. I will not be reading his resume following every award, but you can imagine the most distinguished awards, you have Professor Liu's name there. He is a member of the National Academy of Engineering and a fellow of IEEE, the American Association for the Advancement of Science, and also the National Academy of Inventors. So with this, I would like to hand this back to Jane Wang, and let's start Professor Liu's seminar. Jane will be our moderator.
So Dr. Liu, would you like to start?
Yes, Jen and Professor Wang, thank you very much for your invitations. It's my great pleasure to be here to talk to all of you. In fact, I do have quite many students coming from Tsinghua, the most outstanding university in China. So it's my pleasure. Let me share my screen and make sure that it works today. So I am going to share with you my slides. And now I share. And also I am doing a slideshow. Can you see the entire screen?
Yes, we can.
You can. All right. So let the story begins. So this is something that my student and I start this scientific discovery journey about more than 10 years ago. That was courageous. If you ask me if I would do that again, maybe not, but we did have very exciting discovery. So yes, I will be tempted to do it again. So today I would like to share with you the story of our journey. Now let's start it from this word wireless AI. You may be challenging that. Everybody say AI, AI. So is this AI or is this what? I think you will agree, speech recognition, Alexa, Siri, and we all call that AI, especially we had this ChatGPT, right? All right. You also agree face recognitions, computer vision that makes sense of image and that makes sense of video are called AI. Yes, we all agree. Now, what is wireless AI? Wireless AI is to make sense of something we cannot see. That is the ambient radio wave around us, the ambient radio wave. We are going to make sense of the ambient radio wave around us to do what? To do many things that we imagine if we can do that before, but we could not, but now we can. Now what you see, this is a real device my company produced. You have a wireless transmitter. And they transmit, you have a line of side pass, you also have many multi-pass. We have all these ambient radio waves everywhere surrounding us. So wireless AI is to do what? Wireless AI is to interpret the multipass disruptions for sensing. No camera, no wearable, no training. To do what? To do all these many things. Okay, so many things that we can do. Now, in the last few years, we have been doing demo to many of the big company. Almost all the big company in many different vertical have been working with us, and many of their chief executive has seen many demo. After they saw our demo, we were commonly asked, is this science fiction or real? Can we do the following things? The answer is yes, it's real. And this is our story. All right, everything started from multipass. And I had already said multipass is everywhere, indoor and outdoor. However, they have not been treated as friends. In fact, they have been treated as a nuisance. Everybody hate them. Everybody try to remove multipass. But everywhere the multipass is different. So when we say we want to remove multipass, that is an ear-post problem. Okay, so now I want to change the thinking. Multipass are in fact our friends, and they all carry all the information that we can use. All right, let's see what multipass is. When we had bandwidth 20 megahertz, this is the starting point of LTE, the 4G system. We had 20 megahertz bandwidth, we can only see so many multipass. If we have 40 megahertz bandwidth, that is the later on this Wi-Fi bandwidth, 40 megahertz, we can see so many multipass. However, if we go to the 5G, 5th generation and 6G system, if the bandwidth is more than 100 megahertz, we can see a very detailed profile of multipass. With such a large bandwidth, with this resolution of multipass, we are able to do many things that was not possible before. If you look at this bandwidth, this is a 5G system bandwidth. So basically, the technology I'm talking about today is belong to the 5G and future 6G system. All right. First, I already explained, the larger the bandwidth, the more this multipass we can see. Now let's give multipass a meaning. Say we are in the center of here, and we had seen multipass coming from many directions to us, everywhere. Let's assume this multipass coming from these directions. We know the time of arrival. So basically, we can imagine that speed of light multiplied by the time, it looked like here, there is a virtual sensor. If we had the other multipass coming from this direction, we know the time of arrival, it looked like in this location, we had the other virtual sensor. So basically, what does that mean? All the multipass can be imagined and can be think of as virtual sensor surrounding us everywhere. But we just never realized that. We never realized there have been so many virtual sensors surrounding us. Okay, then if we treat that as a virtual sensor, then we have new degrees of freedom. Every multipass can be considered as a new degrees of freedom. And there's a large number of degrees of freedom exists in our surrounding. It just, we never know that before, and we never know how to utilize them. All right, question now. If we think of that way, how can we harvest multipass? We have to rely on physics, power, and bandwidth. Power, we cannot do anything about that because the government and standards say it's only 1 watt for Wi-Fi. So the power is limited. In fact, the larger the power, the more this electromagnetic wave can bounce back and forth. Okay, so there's more multipass, but we cannot do anything with it. Bandwidth is getting larger and larger. 5G, 6G getting larger and larger. So here's the good news. Okay, it's related to the bandwidth. All right. How can we control all these virtual sensors? We had to also rely on physics to do that. Here, I want to introduce a physics or time reversal. The physics or time reversal say this. Here we have a transmitter. If a transmitter transmits a pulse, what happens? Receiver is going to receive a profile of multipass arrive at different time. Time reversal physics say if we time reverse it and complete conjugate, and then we let the last one go first and the first one go last, and send it back one by one, then all of them are going to arrive at the same time at that particular location. Coherent phase constructively add up all together. It's an energy ball. They all come together there all at the same time. The more multipass, the better. Now, here is our experimental result. You can see that at that particular moment, all the energy come together add up. That will be a 6 dB bandwidth. Okay, 6 dB. All right. Now, this is the simulation result with more than 100 megahertz bandwidth. It is an energy ball. Whenever the bandwidth is not large enough, we cannot see enough multipass, so we cannot see a clear this energy ball. This is a experimental result. This is a real experiment. This is a 0.5 meter. So at 5 gigahertz microwave range, this is a 1 to 2 centimeter energy ball. So we show that it is possible that we can have this time reversal effect in our real indoor environment. And if you want to imagine what does it look like, it's energy ball you cannot see. But if you drop a ball, a stone into a pond, you can imagine this is a two-dimensional one. Okay, so now we can do this time reversal. So what will be the first application that we can do? In our experiment, we accidentally found that we accidentally solved a problem that the whole world tried to solve for many decades cannot. That is an indoor locationing problem. Where are you indoor? That problem has been very difficult because many of the solutions try to use line of sight triangulations. We come from a completely different paradigm. So now let me show you. This is the world first centimeter indoor locationing. There's a result under the non-line of sight condition, meaning it's a non-line of sight condition. You cannot see the other side. It is many rooms separate away. This time reversal can be 1 to 2 centimeter. Most of the existing scheme mostly is about 1 meter or beyond. And 1 meter is a curse because they only have 2 to 3 degrees of freedom. And even under the line of sight condition can be only 20, 40 centimeter. Doesn't matter which condition, we are always 1 to 2 centimeter. This is based on the real physics. And next, I'm going to show you a demo. So pay attention to this. This is a wire. This is the time reversal transmitter we built with the 125 megahertz bandwidth I mentioned to you. Look at this. Okay, this is a trend. We move away, 1, 2, 3. There's a separate by 3 wall. Here, this is the other single wire here. That is an antenna. 20 meters away, separated by 3 wall, we are going to track this single wire here. So the train is running here. We need to let the train to go for a complete loop. And we sample at 100 Hertz. At every location, we are going to collect the channel impulse response, okay? So that we can know exactly where they are. So now we let it go for 1 loop to collect the channel impulse response as a fingerprint. Okay, 1 loop already. So we need to put this back to the origin, the starting point. So now it's a starting point. All right. Now please look at here. This red dot is our real-time estimate. We didn't use supercomputer. It's a very simple data. Compare this and the wire here. You can see that we can track this this antenna. A single wire can track a single wire 20 meters away, separate with a 3 wall. Now you can see even better what we can. All right. So what you see this is something that we had done in 2015. This is something that before us, the whole world tried to solve, but cannot resolve this problem. We accidentally solved this problem from trying to tackle a completely different problem. Anyway, so we can do this tracking. But now you may ask, can we track people? The answer is not, because I just mentioned we need to do the fingerprint, right? And we need this device. So question, if we want to track a person that we cannot pre-training with this fingerprint, what can we do? Remember, now go to the next. Remember that we said this is the energy ball. So I asked my students, let's look at this ball, because when bandwidth is not enough, it looked like cloud. It looked like there's a structure. Let's look at that. So you know what? We prove this energy ball is not a point. It is not an energy point. This energy ball has a structure. The energy distribution is of Bessel function. So this is the Bessel function energy distribution. This is a theory. This is our experimental result. And we prove, there is a level here because of the line of sight energy. We prove that it is true. Now, we cannot measure the power because in real application, we cannot actually measure the power. So what can we do? We also show that we can use the second order statistics. The second order statistics of the channel impulse response, and we know the second order statistics basically is a measure of energy. So if we define a second order statistic we call time reversal resonating strength, then it is also of Bessel function. Here's the good news. This Bessel function is true in Washington, D.C., in Tokyo, in Beijing, in everywhere. So with this, we can track people. What does that mean? They say at time 0, I'm here. When I move, I will have a new CIR or CSI. Okay, CSI, channel state information, is a Fourier transform of CIR. And now if we receive a new one, then I can do correlation to see where I am at a correlation level. Say it's here. Then if it's here, then I will be able to know how far I move. I know the time, so I know the speed. So in essence, we are able to estimate speed reliably indoor. That is not possible before. Okay, so this is a major breakthrough. Now, you may ask, here we need an active source. How about if passive source, a human being is walking? Can we estimate the speed? Yes. We also prove that the autocorrelation function of this AM-EM wave is also a Bessel function. You know why? That is because when we are walking, it appears we have many virtual antenna on us, and they reflect the speed that we are walking. So if we view this as a collection of many virtual sources, then the collective strength can be revealed from the statistic, and it is a virtual time reversal effect. So again, it is also a Bessel function. So now with active source or virtual source, it all got unified together. We are able to estimate speed precisely, accurately indoor. So what does that mean? That means what we see here is we need many multipaths. The more multipaths, the better the performance. So basically, this is a new paradigm that defines any prior scientific belief, because before, almost everyone working in sensing communication, we all try to remove multipaths. We consider them as a nuisance, as interference. But here we are saying the more the better. So basically, we have uncovered a science that is ideal for indoor application, because the more multipaths, the better. I didn't realize the following until my friend, I didn't know him before until he did this article for me. He is with JPL and Caltech and editor-in-chief of this IEEE Journal of Microwave. He's a physicist. He said that this time reversal technique represents almost a 2-century-long quest for some new physics that could equal or rival to Doppler effect, because Doppler effect failed to be able to function indoor because there are so many multipaths. Even though Doppler effect can be used outdoor, in satellite, in airplane, in missile, everywhere, but it cannot work indoor. The time reversal we discover here cannot work outdoor. Without multipass, it fails, but indoor is perfect. So these two physics, in fact, are hand in hand that can offer unlimited number of applications. All right, now with this, we are able to estimate speed indoor. I'm going to show you something that cannot be achieved before. Here is the headquarters of Marvell. You know, Marvell is a very big company, silicon company in Silicon Valley. This is their headquarters. It's a 50-meter by 60-meter wide, and this is a gigantic building, okay, with open space, and you can see there's many these cubicle here. So we arrive in the morning and we put our satellite here. Satellite is a Wi-Fi. It just do the ping, 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 ping signal. That's it. And once we have that, then we can start to do tracking. Before we start the tracking, they told us, you don't work yourself. You have to follow our people because they worry that we may be doing some kinds of cheating. So we have to follow their people. In the next two demo, I'm going to show you the real data we collect there. All right. So this is the wrong one. Now pay attention to this. You can see that they try to do all the trick to fail us. We had two group of people because we told them we can track unlimited number of people. So we had two group independently working. All right. This is the wrong one. And then this is the wrong two. Now I would like you to pay attention to this person. You can see he tried all the trick he can to fail us, but he couldn't. All right, we walk 3 times, and also we demo them many of the wireless sensing that I'm going to show you later today. We got a standing ovation from more than 100 people. In fact, we also do similar demo to Qualcomm headquarters, to their CEO, and also Apple headquarters, to their VP. They could not believe that we can do this tracking. All right, now I want to go to the next one. Did I say that we can estimate speed, right? So what can we do there? So let's start it from this. This is also a real demo that we did last year in January in CES. This is our employee. This is in Venetians. So we demo this to many company. We detect human. How can we detect human? Because we can detect the speed. With the speed, we can pick up the gait pattern, gait, G-A-I-T. Gait, and we are bipedal, so we are very distinct in our walking, so we can determine it's a human being. Now he walk away. We have a mechanical fence, so it's non-human motions. Now, okay, and then next you will see he come back and his motion dominates, so we detect human again. Next, you are going to see the gait data I mentioned to you. Here you can see the purple signal, right? That is the real speed that we estimate. You can see the speed we estimate here. This is his walking speed. So when he is walking, we can even not only we know the speed, we can know the stride length and also the cadence. The cadence, I mean, how many steps per minute. You see now he is running without any wearable, nothing. It's all from the Wi-Fi ambient radio signal. All right. Then some of our partners say, you can detect a human being. Can you filter out the animal? Why? Because in many security applications, animal is the problem. Why I am doing this? Let me go to the next. Okay, the animal. You can see this is pet. It's not bipedal, so it's a pet detect because its gait pattern is very distinctly different from human being. So this we can detect a pet. All right, so we are able to filter out animal motion, and therefore we can reduce false alarm dramatically caused by animal. All right, now let's talk about fall down detections. Remember, we can estimate speed accurately. So the acceleration is a derivative of the speed here. Now, fall is a very distinct motion. Why? Because all the way we have the earth trying to pull us down. So there is a G acceleration all the way. And suddenly when we hit the ground, there's a -4 or -5G. So it's a very distinct motion. In what sense? If you look at the change of acceleration and also the maximum speed, The fall is here in this region. All the other human motion are in this region. Therefore, it's very distinct because we can estimate the speed accurately. So with this, we are able to detect fall with very high accuracy. Now, this is the testing that we had done with Best Buy. We had so many total fall, and the catch rate is 90% with a very small false alarm. At the same time, we also compare with Apple Watch. In this case, Apple Watch, the detection rate only 25%, and all the other methodology only about 50%. This is the only one can achieve such a very high accuracy rate with such a low false alarm. Now I want to show you a real demo. This is something that we actually did a real demo to Samsung in our one of our employees' house, because we can cover the entire house. So they require us to
Demo
demo
starts.
at two different locations that cover the entire house. So now you can see the employee is working and there's no false alarm.
Fall down. Fall down.
That is
Fall
one
down.
location.
Fall down. Fall down.
Now he is going to move to the other location. It all covered by the same device.
Fall down. Fall down.
All
Fall
right.
down. Fall
Okay, I
down.
guess you get the point. This is a real demo to Samsung. Now, when we are breathing, even though our chest have very minor motion, but there is a motion, periodic motion, and the electromagnetic wave pinching on this can sense the difference. It can be picked up. So we can pick out the breathing. If we can pick out the breathing, then we can monitor sleep. Do you know why? Because sleep can be divided into two broad types. One is called rapid eye movement, it's called REM, and non-rapid eye movement. So what is REM? REM is when we are sleeping, we had a dream. When we have a dream, our eye will move rapidly. It's called rapid eye movement, and our breathing will become very fast. So with that, we can detect the REM stage and non-REM stage, and also awake. Okay, every night we had to have 4 to 6 such a REM stages, so that would be a good night. So we are able to pick up this and also determine the quality of sleep. With motion and breathing, we can build an analytic. We can determine the sleep stage. This is a real data collection that we work together with the Taipei government. They have a single elder housing. So we put this into their house, a single elder house. And they say that to determine an elder person, how many times go to the bathroom per day and how long they stay is very important. So we put one device there. Now you can see this is the sleep. Is go afternoon nap from 2 o'clock to about 3:40. That's a 2 dream, pretty good nap. And it go to bed at around 9:40, and then with so many REM. And this is the stage. And how many times go to restroom? So many times, and this is the duration of their stay. By the way, this is a radio, so we cannot watch. Nobody is watching. And then this is the next day. You can see it went out for the whole day. And well, also a nap, a shorter one in the afternoon. And this is sleep, and during which it go to the restroom at one time. This is all without wearable. It is just a Wi-Fi device in the house, and we are able to pick up this live log. Okay, that happened in 24-hour day. Now, as you may tell, most of the car now have Wi-Fi. So the Wi-Fi inside the car, we can detect the motion and detect the breathing, so we can determine if a child is inside a car or not. This is something that we work together with Ford Motor company and also the other tier 1 company. With so many different vehicles, so many hours, and the detection rate is 99% with a low false alarm. We are able to determine if a child inside a car or not simply by using Wi-Fi. No child need to die again inside a hot car. All right, so that is application. And by the way, do you know that you and I, not only we look very different, our entire body is very different. And this radio wave impinging on us also have many different kinds of refraction and diffraction. So we are able to determine different people. It's through the wall, okay? No radio need to be inside this room. So what you see here is there's a footprint here. A dozen people will be standing here. A transmitter will be here, receiver will be here. There's no sensing device inside this room. We are able to recognize a dozen of different people with a very good ROC curve. So this is to show that this can be also treated as radio biometrics. All right, that is based on 5 gigahertz, 2.4 gigahertz, this microwave range. Now let's go to millimeter wave range. By millimeter wave, we know that the wavelength is millimeter wave, so it can be more accurate. However, it cannot penetrate the wall, so this is mostly line of sight, this Wi-Fi radio. Now, look at this. What did you see? It looked like a ghost, right? This is imaging without optimization. So basically, through radio wave, without optimization, we can see a ghost, something like human being. Once we optimize, this is our result. This is our benchmark. This is a Kinect. As you know, Kinect had 2 cameras. We can compare with camera. This is simply our Wi-Fi. We don't have any camera at all. We can do this imaging. Again, it can be through this very simple wall. That can be possible. That is many years ago. I think our paper I did this year. This is many years ago. Now, our most recent result is we are, by using deep learning, not only we can reconstruct a figure, we can reconstruct a human image as close as the Kinect, okay? And from here, we can even recognize a person. Here is 7 and 5 people, not that many, it's just a beginning. We can have very high accuracy rate. So this is about using MMA Wi-Fi, or you call it radar, doesn't matter, it's the same thing. We can do imaging, and the performance can be not as good as camera because it's optical, as you can see, but it can come close. So with this millimeter wave, no wonder we can do tracking. At the same time, we can track many people. Given its accuracy, our tracking accuracy can be less than 10 centimeters, and certainly we can track many people. Okay, this is no surprise, but I want to show you this. Did I say millimeter wave, the accuracy is a millimeter? With that, we can track handwriting. So this is the actual word that we write, okay? This is the actual word that we write. This is the reconstruction from our tracking of the hand movement. So basically, we can write anywhere. And whatever we write, it can be captured because we are able to track the hand movement. And now, I mentioned we can pick up breathing. That is using 5 gigahertz, 2.4 is Wi-Fi. When we come to the millimeter wave, we can pick up the heartbeat. Heartbeat is so tiny and emotions, okay? So now it's a radar, it's a millimeter wave. So we can see these 2 persons at different locations. We can identify the location, breathing rate, heartbeat. And we can tell this the men and women had different breathing rate and heartbeat, and we can pick them out, and you can continue to see. All right? So, because we can pick up the heartbeat, therefore, we are able to determine the heart rate variability, right? Heart rate variability is a very important health index, especially during the pandemic, all right? So this is something that we also can do. And in addition to that, keystroke, we can do typing. You type in on computer as an input, or you type this keystroke. Because of the accuracy, no wonder we can do that. I want to show you the video that we have here. All right, I think that you got the point. This is the 60 gigahertz, this millimeter wave radar that we are using. All right, now, this is something that I feel pretty exciting about. By using millimeter wave, we can pick up sound also. Really, we can pick up sound. we don't need to use acoustic microphone. So this is the demo I'm going to show you. Oh, not this one. It should be this one. This is TI 77 gigahertz millimeter wave. Okay, now what you hear is picked up by acoustic microphone, as traditional one. The next, this is going to pick up the vibration, the membrane vibration from here. Okay, all right, that is from acoustic wave. Here is the pickup by this guy. All right. I think some of you may say the quality is not as good. Agree. The reason is this is a membrane. When you have a membrane, it's like a low pass filter, so you lose the high frequency. But that's not the point. The point is we can pick up all the vibration. We can pick up all the vibration from there. We can reconstruct sound. So vibration such as aluminum and also plastic bag. As long as it's a vibration with any sound, we can pick up from there. Now the next one I also found it pretty interesting. Now you are going to see what? The next one, oh, not this one. Okay, the next one. This one, we are going to take out all the background noise because what? Because this millimeter wave can pick up our voice from our throat, the vibration, and we treat that as the source, okay, as a reference signal. And every background information can be taken out.
There was once a young rat named Arthur who could never make the trouble
Now
to
the
make up his
background
mind.
noise are taken out.
Whenever his friends asked him if he would like to go out with them, he would only answer, "I don't know." He wouldn't say yes, and he wouldn't say no either. He could never learn to make a choice. His aunt Helen said to him, "No one will ever care for you if you carry on like this."
This can be used to allow us to be able to talk anytime, under any condition, into our smart phone, and the other side can hear crystal clear because now we can take out all the background noise. The ambient noise can be completely taken out, including under a very loud this noise condition. Now I guess you may agree with this. We can have many applications in home security, home monitoring, home automation, activity, sleep, and fault detection. There's many applications, and there are many things can be done. Not we can do. We would hope that many companies can pick it up and then build analytics along this. And you can tell the applications can be unlimited. I hope I convince you why this is a new sixth sense that we have. Because in addition to what we can see, we can smell, we can touch, this is something that we can use to sense our environment and can decipher the world. Then your next question will be, all right, man, it's so great, but this is research. Have this ever been used and deployed to the real world? The answer is yes. This is something that we deployed in 2019. Linksys, you may know Linksys is a very big Wi-Fi company. They are our investor. We work with them, and as Linksys aware is to be able to secure a house when you are not there. By the way, this is a Wi-Fi system. At the same time, it can also do sensing. So it is an integrated communication and sensing system. This is the world first one that has been deployed as integrated communication and sensing system. All right, next. We also work with Verizon that have been deployed as a home awareness. Verizon, this Wi-Fi home router can also protect home. At the same time, we are working with Deutsche Telekom and also T-Mobile to deploy in Europe. Now, this is the testing result from T-Mobile with so many different environments, so many days, so many hours. This is the detection accuracy with such a small false alarm. This is beyond their expectation as they told us. All right. Now, this is something very interesting. We work with Philips. This light bulb, and Philips, as you know, is the largest light bulb company in the world. They have 70% market share in the world. So basically, many of the future light bulb will be Wi-Fi enabled. and the light bulb will be able to turn on and off by itself for energy. There's energy management, and also it can monitor fault detection and human well-being in the future. That is something that we are working with them. We are also working with a carrier that is the largest HVAC company, air conditioning heater company in the world, that we can also provide energy management. As you can tell, many of these light bulb and this energy consumption that we have, indeed, it create a lot of this climate change, this crisis. So we hope that we are able to help a little bit from this particular point of view. And this is for security company. We are working with the largest security company in US, largest security company in Europe, and this #2 security company in US to deliver this solution to replace the traditional security system. Along the way, we also have won many awards along the way, thanks to our team member who have been dedicated. So we won quite many awards. If many of you have certain interest in what we have been doing, especially in early day, we do have a book that summarizes some of our fundamental results in this wireless AI sensing book. All right. I hope that I have convinced you. Now, the ambient radio wave is indeed the new sixth sense that will help us to revolutionize our life in the future. Thank you very much for your attention. Thank you.
Dr. Liu, thanks a lot. Really wonderful talk. So now the floor is open for questions. I think in the chart, Dr. Liu, can you look at the chart? There's one question, it's pretty long, so might be good you.
All right, which one?
In chart, the question is that can algorithm distinguish between exercise indoors and fall down? That's #1 question. You have a fall detection. The question is whether it can distinguish between people are doing exercise voluntarily or it's a
Yes, we have never, as you can tell, let me explain why I say yes, even though I had not done that, but my instinct say that is not that difficult. The reason, if I can find the full thing, the reason was
this one.
here, okay? The reason was, look, fall is a very distinct motion because fall, when we falling down, the earth continue to pull us with the oscillation G, okay? Not our outer motion had such a continued oscillation G, and suddenly it will stop with a -4 and -6 G. So you can see the change of oscillation is dramatic here in this particular motion. For all the other motion, it just mostly changes in this speed, not that much in the oscillation. So I tend to think that these other regular exercise that we have, it had periodicity. It also had regular motion that can be very distinct from the fall detection. Yeah, it's just my gut feeling.
Thank you.
Hi, can you hear me?
Yes.
Yes.
Yes. Hi, good morning. It's a very great presentation, Mr. Reilu. So this is the earlier question Ms. Jane asked is from me. So thanks for the explanation. And my second question is like I myself used UWB real-time locating systems for position tracking of the people and the equipment. So can you compare the accuracy of existing solutions of UWB with your solution in terms of, let us say, whether we get 1 centimeter accuracy or 10 centimeter accuracy or 20 centimeter accuracy? Can you just give your view on it?
Ultra wideband is a short range line of sight application, line of sight.
Yeah.
And what it can achieve, that is many years ago, is 20 centimeter under a line of sight condition. You need to have 3 directions to do triangulation. That is a very old technique. they cannot perform. They fail when it is non-line of sight. So when you separate by one wall, not to mention 3 wall or the different room, it fail, it cannot function. Using time reversal, it can function line of sight or non-line of sight condition, always 1 to 2 centimeter. There's no problem at all. So there's a big, very different. And also the mechanism, the way that we determine the mechanism is very different. In that time reversal, the degrees of freedom is hundreds of thousands of degrees of freedom. But triangulation only has 3 to 4 degrees of freedom. So it's very different techniques.
Okay. So the current solution that you are providing, so does it has like a 1 centimeter accuracy or 5 centimeters or 10 centimeter accuracy?
It's 1 to 2 centimeter using 5 gigahertz. If you use a millimeter wave, it has been reported the accuracy will be millimeter. And we can also track writing. Okay, that is also at that level of accuracy.
Okay. Thank you. Thanks a lot.
Professor Liu, this is very interesting. I also have 2 questions. The first question is, did you actually compare like your new technology with existing technologies for sensing like a person's movement or vehicle's movement? What's the cost difference, through your test?
There's no existing sensing technology. Everybody want to do this. Nobody can. Especially under indoor environment, because indoor environment is so many multipass. So there is a very big computer science community trying to do this, but everyone try to come up with a heuristic algorithm, in my opinion, a heuristic algorithm under their particular scenario, under their particular problem, in their own lab condition. They can prove it work, but it cannot work under many different real conditions. Because this is a physics inspired. We have uncovered a physics that can estimate the speed. We can detect the motion with this sound physics that we can have, together with the signal processing and AI machine learning that we all put together. Therefore, we are able to do so. It all because of the physics that we have. Therefore, what we propose is not a heuristic. So, yes, up to now, we are the only one can use the Wi-Fi, the existing ambient radio wave, to be able to detect and this motion and to decipher the world. Certainly, they have some other people using millimeter wave radar or very special equipment with many antenna array to do so. But our philosophy is this: the ambient radio wave already everywhere, like Wi-Fi, 5G, 6G. So we try to rely on the existing one to be able to do so.
This is wonderful. I'm in the traffic engineering field. We certainly need to collect such data. And for example, to sense pedestrian movements, right? This could be indoor or outdoor.
Yes.
And the video is a common technology, but when people are occluding each other, video will not work very well. So I wonder if your technology will be able to separate a group of people walking together with significant occlusion.
Okay. Yes and no. Let me tell you which one. Let me say yes first. So if we are using millimeter wave radar, millimeter wave basically is a 5G or 6G is basically using millimeter wave, because millimeter wave is the wavelength is so short, but it is line of sight. It cannot be non-line of sight. It can, I already showed in one slide, I went through very quick. We can monitor many people at once, no problem at all. And there's no camera, so it's very good for privacy reason. However, if we want to use 2.4 gig or 5 gigahertz Wi-Fi, meaning something that we are using today, that we cannot distinguish more than one people, because different people, the signal can be corrupt and we are not able to distinguish. Nevertheless, it can cover the entire house, because it can penetrate the wall, and that can be used for applications such as a single elder person who live alone, and we can do fault detection and well-being application for the person. But when you have multiple people, especially if they are in the same room, then it won't work. It will be all mixed together. So depending on which wavelength you are talking about, and then we can use that for different applications. Yeah.
Thank you very much. That's very interesting.
So other questions from, I think people can ask it directly. Thomas, you can ask a question directly.
So there are questions in the chat box, Jane.
Yeah, oh, okay. Thomas, is Thomas here or I can read? So number one question is how robust is the algorithm since it's using the waves signals? Can it resist from the signal attack? Like add some interfere signals, let receiver get confused. It's more like an attack, try to confuse the receiver or change the layout of the room by moving huge furnitures like sofa and cupboard. Robustness about the algorithm.
The beginning, when we were doing this fingerprinting approach, that require training, that require fingerprint. So when the environment change, we need to redo the training. But after we can use the speed information, everything after that, we don't need training. So it is environment independent. With a focusing ball, I say, is using the Bessel function. So it doesn't matter because the only condition we need is that there's a large number of multipaths, it come together. We don't care what multipaths. So it is environment independent. Therefore, it doesn't matter. Yeah.
Okay. The second question, I think, is kind of like similar to what Professor Wang asked. How many people can this technology track? Can it track some special guests in a busy store when all other customers
Yes.
are doing random walking?
We can track unlimited number of people. You see the demo that we have, we can track 2 people, right? Do you know why we track 2 people? Because we say we can track unlimited number of people. And the reason is this. Look, we just need to have a satellite. Satellite will do ping, 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 and that is a Wi-Fi signal. Everybody listen to the Wi-Fi signal and then calculate their speed information. So basically, it's just like our GPS when we were driving, right? We just calculate our own speed and direction. So everybody do it their own. We don't have a centralized place to calculate for us. Therefore, everybody do their own. Everybody can be tracked, and there's an unlimited number of people.
Excuse me?
Yes.
Yes, go ahead, please.
Yeah, yes. The third question is once the algorithm is get corrupted, so how long does this algorithm recalibrate itself? You say you're going to retrain everything and
I don't understand your question because what do you mean by corrupted? Okay, I don't understand that. And also, what do you mean by retrain? So you may want to make it clear.
so if we change the layout, like the layout of the room, so if we move
it's
some,
independent. It's independent. There's nothing.
okay,
It's no relationship to the layout. Look, we have deployed our product
okay,
to millions of households worldwide already. So we cannot know every single house. All right.
sure.
So our method, the user, they don't need to train again. It's just like you buy a Alexa going home, you turn it on, it can work. So it is environment independent. Nobody need to do training, and so it will not be affected by you changing the
Oh, I see. Okay, thank you,
Oh,
Dr. Liu.
Yeah. Dr. Liu, a follow-up question. When people first initially first time use your setting or device, do they need to do any calibration? Initial calibration?
No.
No. Okay.
Yeah.
Thank you. Any other questions? Actually, we're running out.
Yeah, Professor Liu.
Yes.
Jason Ning here asking a question. So I think the topic you covered just now, I think that there are 2 topics. One is it's like using reflection waves to like locate an object. And the second is I think for the acoustic application, I think it's like using direct arrivals to detect the acoustic signals. Is that correct?
No, we didn't pick up the energy from the acoustic wave. That is a traditional acoustic microphone. What we pick up is we look at the vibration of membranes. Okay.
So conceptually, it sounds like a single pixel camera, but using microwaves, right?
You can think that way, but from my point of view, basically we can pick up tiny motions, tiny motion in the millimeter waves accuracy. And because of that, all of these very tiny motion that carry the sound information still embedded there. And we can use some signal processing learning technique to recover that. So basically what we need to pick up is that kind of tiny signal at a millimeter wave. Yeah.
Yeah, thank you. And also a follow-up question is that, for example, in my application, so the source of the signal and also the source of the noise, I mean, they can be connected by some medium. So inevitably the noise will leak into the location where the source is located. So in this case, I guess we will still not able to completely separate the signal noise, right? So there'll still be some residuals in noises.
No, in fact, you can look at my paper because I can tell you almost every slice that I present is an IEEE translation paper. So you can find all of the paper there.
Thank you.
So so let me expand a little bit. The separation, basically, we can pick up. So if you have a smartphone here, you can pick up our voice from here. And that voice, even though it's not perfect, but it can serve as a reference signal. Do you know that this voice and noise separation, the reason it had been so difficult was before there's no reference signal. It's a blind signal separation. It's an ear post problem. That's why it's so difficult.
Oh, I see.
Yeah.
I see.
And now, if I can provide a reference signal, the problem has been reduced. So first, I offer a multi-modality. This two modality can reduce the complexity of the problem dramatically by 2 orders of magnitude because we have the reference signal, and therefore all the background noise can be removed. We are now talking to many, I cannot tell you now, the manufacturer for the smartphone to see if we can have this technology to be used in a smartphone, because under any condition we can talk, and then the voice quality can be crystal clear under any condition now.
I see. It's like to inform a blind separation problem.
We transform from a blind separation problem to a traditional this signal separation with reference signal.
Yeah, thank you, Professor Liu.
Yeah, thank you. I think we are almost running over of the time. So anyway, if people are interested in, you guys can check our TAAC website and get Dr. Liu's contact information or any follow-up questions. Due to the time limit, I think we are concluding today's TAAC distinguished talk.
Thank you very much, Professor Liu.
Thank you for having me. Thank you.
Thank you
Thank you very
everyone.
much, Professor Liu. Eye-opening talk.
Yeah.